In my previous video, nerds61, I found an error in the signal analyzer function, the function that I use to measure sideband noise of oscillators split into phase noise and amplitude noise. In this video, I will try to verify that finding or maybe falsify it and change Linrad accordingly if required. So to that end I have arranged like here the Wenzel oscillator, a very good oscillator at plus 13 dBm 10 MHz, then 100 decibels of attenuation. After that, several amplifiers with about 70 decibels of gain together, series connected noiseless feedback amplifiers. And then the hybrid with a 50 ohm resistor and the 2-channel receiver. First I run as a normal receiver, as a spectrum analyzer. I have calibrated Linrad carefully, so I have the signal here at 10 MHz. DC is here about 700 or 750 Hz below. Sorry, that is here, the notch. And here is the mirror image. The level of the signal here is calibrated to show 0. I have set the bandwidth carefully to plus minus 500 Hz. Well, it's easier to see like this, 500 and 500. And then I can verify that, while the signal is at 0, the dBc per Hertz is 30 decibels below that. The average of the two channels is 29.989, and the channels are 29.96 and 30.01. And of course the difference between these two is the same as the difference between these two. Now when I click at some offset frequency, let's say here, then I see the noise floor. And I wait for a while to get it more carefully. Well, here it is minus 79.5 dBc per Hertz. 79.55. And this was 1.1 kilohertz. I go for 10 kilohertz. And it's hard to see where I changed the frequency. I think it was here. So I wait a little. You can see on the main spectrum that the noise floor is very flat. Note there is only half a dB between the divisions on the scale, so it is flat within 0.1 dB or better. That's because of the calibration, of course. Now I must have the new value. Here, minus 79.56. This is 10 kilohertz. That is just 0.01 dB difference. So I have minus 79.55. And that is dBc per Hertz, and it's the sum of the phase noise and the amplitude noise. The noise here is the white noise from the amplifiers, and any sideband noise from the oscillator is far below, and also any flicker noise from the amplifiers is far below these levels. I'm running in correlation mode 1, and it has collected 7,000 averages. But the correlation advantage is 0.02 dB. Actually it is 0, but I didn't set levels absolutely correctly. There are, is it 0.3 decibels or something here that differ between the channels. That is part of the explanation for this not being exactly zero. And also the noise, because this is the difference between the correlation spectrum, which is very accurate, and 1000 averages of the power spectra. The mirror image, which is pretty strong in the waterfall here, it's really not strong at all. You can see in the graph here. And if you look at the noise, it isn't much stronger than the white noise. I have here now -79. So introducing also the mirror image lifts the noise floor by 0.55 dB only. So this is perfectly okay to neglect. With the composite noise measured as the total power on one side of the carrier at -79.55, the phase noise has to be -82.55, and the amplitude noise has to be the same. I have set Linrad now for correlation spectra mode 2, and here is the signal analyzer graph after 2.5 minutes. I see 80.5 approximately. That's wrong by 2 decibels. If I look at the phase noise only, we can see that the power spectrum here, the two channels, they are identical, as one should expect, because the noise from that amplifier chain is stronger than everything else, except for the carrier, which wins a little bit above them. This notch is at about 700 Hz. It's DC from my direct conversion receivers. Here is the mirror image. Why the floor is not perfectly flat here, I don't know. Maybe I can use more averaging. I don't remember how far I can go with this. 2047. So I have to wait until it has actually collected that. I have expanded the scale and waited long enough. The average power spectra are at 83.6 and going up and down by up to 0.2 dB. And the correlation spectrum for the phase noise is at 80.6. A little bit less variations with frequency. But the difference is 3 decibels. That's quite clear. Now the level 83.6 is incorrect by almost 1 dB. And I looked at the amplitude noise, and this is at 80.6, well, minus 80.5. And the same is here for the average power spectrum, but this is at close range. Maybe there is something with some AM noise from the amplifiers. At wider separation it is 80.6, and then my system falls off about 1.5 kilohertz with these settings, and 83.6, it's about here. So I will correct the code in Linrad to make this errors much smaller, or hopefully insignificant. 8,000 averages. The phase noise is at 82.55 approximately, here somewhere, and the AM noise is similar, and here is AM noise and phase noise at the same time. So I think I have corrected now the mistakes. 3 decibels, that was a stupid mistake. 0.95 dB, that was setting the bandwidth incorrectly of the transforms. I had set simply 5 Hz and it looked good enough, but it wasn't. It's a little bit below 4 Hz. Here is phase noise at a more normal scale, 5 dB per division. The imaginary part is down here. AM noise, very similar,